This video is on the properties of liquids. We're going to start off generically just talking about liquids in terms of shape and volume, particle movement, and particle distance. Liquids traditionally have defined volume and what we call indefinite shape, which means that we can actually measure the volume. The volume of the liquid doesn't change regardless of the container, but if we take a particular volume of liquid and we take him from, say, a graduated cylinder into a beaker, the shape of that liquid would change, but the volume would stay the same. For liquids, we say that the particles now have an ability to flow and that the kinetic energy is medium. It's in the middle. Liquids are at a medium temperature. They're warmer than solids and colder than gases. And that the particle distance, I'm going to use the term there at a Goldilocks distance. They seem to be just right. The particles are linked to each other, but they still have the ability to flow and slide past each other. And usually, liquids are less dense than solids, but more dense than gases. They're always more dense than gases, but there is an exception to the rule of liquids being less dense than solids, and it's a very, very common substance that you deal with every single day. Okay, we also have some additional properties of liquids now that they start to have this ability to flow. The first one is compressibility. Liquids are considered incompressible, that you can compress them just a little bit, but we consider them incompressible for all practical purposes. This comes in handy for things like hydraulic pumps and brake fluid, things that you need to lift heavy things or stop heavy things, such as your car. We like to use liquids there because we can build up a lot of pressure, and if you remember, pressure is force per unit area, so we can really apply very large forces with liquids. The next one is fluidity, and liquids, because they can flow, we start grouping liquids and gases together and call them collectively fluids, meaning that they have the ability to flow and diffuse. The next property that we're going to talk about is viscosity. Viscosity is defined as the resistance to flow. So if a fluid has a very high viscosity, it has a high resistance to flow. If it has a low viscosity, it has a low resistance to flow. And materials that people traditionally think of when they think of high viscosity fluids, they think of honey and molasses and somewhat syrup at room temperature. Low viscosity fluids, water is the classic example of a low viscosity fluid. But syrup is interesting because at room temperature it's pretty sticky, ooey, gooey, doesn't really like to flow. You have to squeeze the bottle a little bit more to get the syrup to come down on your pancake or your waffle or whatever you're using your syrup for. But if you stick it in the microwave and you heat it up a little bit, the viscosity starts to drop and it starts to become runny. So these are all adjectives that we use and when we're talking about viscosity. Ultimately, though, viscosity depends on a lot of things. It depends on temperature. It depends on intermolecular forces, which we'll talk about a little bit later. And it depends on the size and the shape of the molecules. Big, heavy molecules, bulky molecules, tend to be more viscous than smaller and more streamlined molecules. The next topic that I want to talk about is surface tension. And surface tension is the tendency for molecules to pull to the interior or for the molecules to stick together and to create the smallest surface area possible. And when we think of shapes that minimize our surface area, what we mean is the tendency for the liquid to become spherical in shape. Then that is the least amount of surface area that it could have for a particular volume. And mercury in particular has a very, very high surface tension. Water has a moderate surface tension, and materials that will just spread out, liquids that will just spread out everywhere and not really kind of ball up or glob together, they would have a very low surface tension. There are things that we can do to liquids to reduce this surface tension, And these things are called surfactants. And surfactant comes from the word surface active agent. And let me write that down for you. Okay, so we've got surfactant, and we have surface from surface, and active, and this is your agent. So these are called surfactants, and they reduce surface tension. And one example, there are many, many surfactants out there in the world, but one example that we have of surfactants is soap. And the last property or properties that we're going to talk about, and we talk about these together, is adhesion and cohesion. And liquids exhibit both of these. And what we talk about with cohesion is the attractive force between identical molecules. And so you think of the co here as things that share, things that are alike. If you cooperate with someone, you're working with them, you're working together. Adhesion is the attractive force between different molecules, and I remember this as Band-Aids, Bandaids, or tape. We call these adhesives because what they're doing is they are sticking two different things together. Tape could be a piece of paper to a wall. The Band-Aids would be attaching the cotton bandage to your skin. So when we talk about adhesive forces, we're talking about forces that are between two different things, and we have cohesive forces that are of similar things. And I want to talk about a few scenarios that can come up when we're talking about adhesive and cohesive forces. So the first thing that we're going to have is scenario 1, and let me make this a little bit, let me make my pen a little bit bigger. Scenario 1, scenario 1. And what scenario 1 is going to be is we are going to pretend that we have some things set up where our cohesion, or our cohesive forces, is greater than our adhesive forces. Adhesive, adhesive. Okay? And so if we have our container here, then what's going to happen is our liquid inside of our container, if our cohesion is greater than our adhesion, our liquid is going to look like this. Okay? Where inside the liquid, there's going to be more attraction. And right over here and right here, let me make these blue and make this a little bit thicker. Here we go. Blue. Okay, we've got these guys here and here. We're going to have more repulsion. Because remember that the cohesive forces are going to be stronger, so these molecules are going to want to stick together. They're going to want to stick to each other more than they're going to want to stick to the walls of the container. And this shape right here, get him a little bit thicker. Let's do this. This shape right here, we have a name for this shape, and this is called a meniscus. And what we mean and what we say is this meniscus here, the shape is going to be concave down, meaning that the arch of that meniscus is in the downward motion. He's frowny. All right? Okay, the next scenario we have, scenario number 2, is when our cohesion, or cohesive forces, our cohesion is less than our adhesion. And again, we have our container here. And now what's going to happen is, because our adhesive forces are bigger, our liquid is going to want to stick to the container more than what they're going to want to stick to themselves. And so we can look at the sides of the container and we say, ooh, right here, there is more attractive forces. Here on the edges of the container. And our meniscus now has a different shape to him. Let me make this a little bit thicker so that way it doesn't look so nasty. Here we go. And our meniscus is now what we call concave up. Okay. And then the last one, you can figure out what the last scenario is. Scenario 3, he doesn't happen very often at all, but let's just mention him. Scenario SCENARIO 3. Scenario 3, again, very, very, very rarely does this happen, but let's just go ahead and talk about him. We have our container, we have our liquid, and this is when cohesion is equal to adhesion. And again, this doesn't happen very often at all. In fact, our surface here is flat. There is no meniscus. Oh, let me erase him because I'm going to run out of space. Erase him right at meniscus down here. And there is no concavity, what we call concavity. No curvature in this interface between the liquid and the gas, air. Okay? And that's all I have for properties of liquids.